So we're going to talk about cooperative binding, which is a very interesting topic when discussing enzyme kinetics. But first, let's review the idea that we can divide enzyme catalysis into two steps. First, the binding of substrate to enzyme, and second, the formation of product. And using this idea, we can derive the Michaelis-Menten equation, which is very useful for quantitatively looking at enzyme kinetics. Also remember that as you increase substrate concentration, the speed of product formation will level off at its maximum value as shown on this graph. Now, the first thing that I want to talk about is that some proteins can bind more than one substrate, and not all enzymes have just one active site. So E plus S can form ES through what I've called reaction 1, but some enzymes can react with another molecule of substrate to form ES2 through what I've called reaction 2, and again to form ES3 through reaction 3, and so on. Now, these enzymes can form product at any stage of this process, no matter how many molecules of substrate are bound. Now, you would expect the rate of reaction 1 to be faster than the rate of reaction 2. If we're looking at the example of an enzyme with 3 substrate binding sites, there are 3 empty sites available for substrate to bind through reaction 1, and only 2 available for reaction 2, so you would expect rate 1 to be faster. Similarly, rate 2 would be faster than rate 3 for the same reason. And the idea is that the active site saturation does not increase with substrate concentration linearly. Now, I get that can be a mouthful, so let's look at it graphically, but we're also going to show an exception to this rule. So in this first graph, I've plotted substrate concentration against the percent saturation of the enzyme, and as you can see, the curve levels off as substrate binding sites become occupied. It becomes difficult to bind more substrate molecules as you have more substrate molecules bound. Next, I'm going to draw a different curve that you also might see in some enzymes, and that's where substrate binding happens more quickly as binding sites become occupied. Substrate binding changes substrate affinity, and we call this cooperativity. Now, with respect to cooperativity, we can define 3 new ideas. Positively cooperative binding occurs when substrate binding increases the enzyme's affinity for a subsequent substrate. Negatively cooperative binding occurs when substrate binding decreases the enzyme's affinity for subsequent substrate, more than you would normally expect, and non-cooperative binding is the same as the first example, where substrate binding does not affect the enzyme's affinity for substrate molecules. So let's look at this graphically. If we have a protein with, let's say, 5 binding sites, and plot the fraction occupied versus the substrate concentration, we would come up with 3 possible curves. The green curve, which takes on a sigmoidal shape, would represent an enzyme with positive cooperativity. The blue curve with a hyperbolic shape would represent an enzyme with non-cooperative binding. And the red curve would represent an enzyme with negatively cooperative binding. Now remember that the effects of cooperativity are only seen after some substrate has already bound, which is why the difference in the fraction occupied between the 3 curves is much smaller at smaller values, like the 1/5 that I've shown here, than it is at the higher values. So let's look at a specific example of a couple proteins. So hemoglobin, or Hb, is the oxygen-carrying molecule that you find in human blood, and it can bind up to a total of 4 oxygen molecules, and it exhibits positively cooperative binding. Myoglobin, on the other hand, which is the oxygen-carrying molecule that you find in muscle tissue, can only bind 1 oxygen molecule in total. And since it can only bind 1, it must exhibit non-cooperative binding, since there's no subsequent substrate to speak of. Now, if we make a graph where we plot the fraction of active sites bound in each of these proteins versus the pressure of oxygen, remember oxygen is our substrate here, and since it's a gas, we're going to use pressure instead of concentration, you can see that the red sigmoidal curve associated with hemoglobin's positive cooperative binding looks different from the blue hyperbolic curve associated with myoglobin's non-cooperative binding. So what did we learn? Well, first we learned that some proteins can bind more than one equivalent of substrate. And next, we learned that there are 3 different types of cooperativity: positive, negative, and non-cooperative. Finally, we learned about proteins that exhibit 2 different types of cooperativity, which are the oxygen-binding molecules hemoglobin and myoglobin.